From deep space, we may have a visitor and has fired up fresh controversy. Again, new thermal gradient images of interstellar object 3I Atlas reveals jets that look shockingly organized.
Nobody was talking about 3I Atlas until the leaked photos dropped. Suddenly, the harmless interstellar comet didn't look so harmless anymore. Within hours, the UN quietly switched on a global defense protocol, usually reserved for situations that never make the news.
Because the American people have both the right and the responsibility to know the truth about unidentified aerial phenomenon. That truth remains hidden, classified and silenced by fear, retaliation, stigma, and confusion.
Telescopes were redirected, agencies went silent, and the tracking priority shot straight to the top. So what exactly showed up in those leaked shots? Why did the UN react like this? And what is 3I Atlas doing that nobody expected? A new scientific priority emerges. When 3I Atlas was first logged in July 2025, it entered the database like any other new comet: position, brightness estimate, provisional designation. Nothing about those early entries suggested it would become a major focus for the world's planetary defense network. But over the next few months, astronomers began to notice something that isn't common in newly discovered objects. The data coming in from different observatories didn't align as neatly as expected. Most comets from our solar system behave predictably once enough observations are collected. Their orbits settle into place. Their activity follows familiar patterns. 3I Atlas didn't. Small inconsistencies appeared in the calculations, and the comet's dust geometry looked different in each set of images. These variations weren't dramatic, but they were persistent, and persistence is what gets the attention of organizations that monitor the sky. By mid-October, the Minor Planet Center had gathered enough reports to justify a coordinated approach. Instead of relying on scattered submissions from individual telescopes, they prepared a formal announcement to bring the world's observatories onto the same schedule. The result was an internal bulletin sent out in late October 2025 asking national space agencies and independent facilities to begin contributing synchronized data on 3I Atlas through the end of January. Nothing in the message implied a crisis, and it didn't need to. In astronomy, consistency is what matters, and 3I Atlas wasn't offering it. The object's interstellar origin made the discrepancies more interesting. Material that formed around a different star behaves differently when it approaches the sun, and scientists wanted a clearer picture of how those differences appear in real time. A structured, multi-month campaign was the most reliable way to capture that behavior. Once the notice was circulated, observatories from South America to Europe and East Asia added 3I Atlas to their tracking lists. Some would monitor brightness changes. Others would focus on its position against background stars. A few would study the unusual dust features already documented by amateur astronomers. Together, their data would feed a continuous record of the comet's motion. Why 3I Atlas became an unusual scientific target. In the weeks after 3I Atlas entered the global tracking campaign, researchers revisited the fundamentals of what they were dealing with. Interstellar objects are rare enough that every new one forces astronomers to rethink assumptions, and 3I Atlas fit that pattern immediately. Unlike comets that formed alongside the Sun, this object originated in a different star system and carries a chemical and structural history shaped by conditions we don't fully understand. That alone made it valuable, but the specifics of its motion gave the object a more unusual profile. The first clue was its hyperbolic path. Most comets follow long, stretched ellipses that bring them back to the Sun over cycles lasting hundreds or thousands of years. 3I Atlas follows a trajectory that doesn't close. It arrived from interstellar space and will leave the solar system again, which means astronomers only get one opportunity to observe it up close. Its speed, more than 200,000 kilometers per hour, reflects that origin. Objects moving this fast are not influenced strongly by the Sun's gravity, so their paths respond differently to outgassing and solar radiation. This matters because comet activity complicates trajectory models. When sunlight warms a comet's surface, jets of gas can push it slightly off course. The effect is small but measurable and normally predictable. With 3I Atlas, the pattern wasn't as clear. Some observations hinted at extra momentum that didn't match the expected shape of the nucleus. Others showed brightness changes that didn't line up with the usual day-by-day cycle seen in typical comets. These weren't signs of anything dramatic, but they were signs that astronomers needed more data to understand how this particular object was reacting to the sun. The comet's appearance added to the interest. Amateur observers began sharing images that showed a distinctive configuration of dust, including a feature known as an anti-tail, where a thin line of particles appears to extend toward the sun instead of away from it. This isn't common, but it can happen when dust spreads along the object's orbital plane and becomes illuminated from the right angle. Seeing such a feature on an interstellar comet encouraged researchers to study how its dust responds to both solar radiation and internal activity. The anti-tail and the first clear signs of unusual behavior. As more telescopes turned toward 3I Atlas, one feature consistently stood out. The comet's dust wasn't behaving the way most people expect when they picture a classic comet tail. In early November, images from observers in Spain, Japan, Canada, and Chile began circulating through research groups. They all showed the same structure, a long, thin streak of material pointing roughly toward the sun, rather than away from it. For anyone unfamiliar with comet dynamics, it looked backwards. For astronomers, it signaled a geometry worth paying attention to. This feature, known as an anti-tail, forms when dust spreads along the comet's orbital plane and becomes illuminated from an angle that makes the line of particles appear to extend sunward. It's not the most common sight, but it's also not unprecedented. What made the anti-tail of 3I Atlas notable was its clarity and persistence. Over several nights, the feature remained sharply defined in images from small backyard telescopes, suggesting that the dust distribution around the comet was unusually well structured for an interstellar visitor. At the same time, the comet's brightness wasn't behaving in a simple, predictable pattern. Most comets brighten steadily as they approach the sun and fade in relatively smooth steps as they move away. 3I Atlas showed variations that appeared slightly out of sync with its distance from the sun, and some early photometric measurements didn't match the level of activity expected for an object of its size. These weren't radical departures from typical behavior, but they were consistent enough to raise questions about how material from another star system responds to solar heating. The shape of the coma, the cloud of gas and dust surrounding the nucleus, added another layer of curiosity. Several amateur observers captured images where the coma appeared more elongated than spherical, almost as if the activity on the surface was concentrated in a particular region rather than distributed evenly. This type of asymmetry isn't rare, but in an interstellar comet, it becomes a useful clue. It may point to compositional differences, structural variations, or temperature-driven effects that don't follow the patterns seen in long-period comets native to our own solar system, tracking a path that didn't fully match the predictions. Once multiple observatories began submitting consistent measurements of 3I Atlas, researchers expected its orbit to settle into a stable solution. For most comets, the process is straightforward. With each new observation, the predicted path becomes clearer, the uncertainty shrinks, and the object's future position becomes easier to forecast. But 3I Atlas didn't tighten into place as quickly as expected. Small offsets appeared between predicted positions and measured ones, and although each difference was minor, the pattern drew attention. Part of the difficulty came from the nature of interstellar material. Comets that originate around other stars often contain volatile compounds that behave unpredictably when exposed to new temperatures and sunlight. When these materials vent gas into space, they create slight pushes that alter the comet's path. Astronomers call these adjustments non-gravitational effects, and they are well documented in comets from our own solar system. What stood out with 3I Atlas was the frequency and timing of these subtle shifts. Some of the early deviations appeared at distances where most comets show only modest activity. Others occurred without strong corresponding changes in brightness, which made it harder to link the motion directly to outgassing. The object wasn't accelerating dramatically or behaving erratically, but the fine-tuning required to model its path demanded a more detailed data set than usual. This is one of the reasons the 2-month global campaign became important. With observations spaced across long baselines, each slight irregularity could be tracked more accurately. Another factor complicating the modeling was the orientation of the dust surrounding the comet. The anti-tail, combined with the asymmetric coma, made it challenging to estimate the size and shape of the nucleus. Without a clear sense of the nucleus geometry, it's harder to quantify how sunlight interacts with the surface. A round, uniform object responds differently to heating than an elongated one with uneven active regions. Early images suggested that 3I Atlas might not be a simple sphere, and any departure from that assumption adds complexity to orbital calculations. A real-world test case. As the early data on 3I Atlas accumulated, one detail became increasingly clear to the agencies monitoring it. This was the kind of object that could reveal how well current planetary defense systems function under real conditions. Not because 3I Atlas posed danger, it didn't, but because it represented almost the opposite scenario. It was fast, interstellar, faint at times, and inconsistent in ways that challenged the tools astronomers normally use to track objects over long distances. For organizations responsible for keeping watch on the sky, this combination made it an ideal candidate for a controlled, real-world test. Planetary defense teams routinely prepare for hypothetical scenarios involving asteroids on uncertain trajectories, but most of those drills revolve around simulated data. With 3I Atlas, everything was genuine. The motion, the brightness variations, the non-gravitational effects, and the compressed time frame available for observation. These conditions mirrored the kind of situation agencies might one day face if a newly discovered object had less predictable dynamics or approached from an unexpected angle. By observing 3I Atlas in a coordinated way, they could evaluate how quickly data flows between observatories, how modeling tools respond to irregularities, and how well predictions hold up under the pressure of real measurements. Another factor that made 3I Atlas useful was its interstellar origin. Objects from outside the solar system don't follow the established patterns that researchers rely on. Their compositions vary, their activity levels are difficult to estimate, and their structural properties are often unknown. Studying such an object in detail helps refine the techniques used to understand bodies that do not share the same formation environment as local comets. This is increasingly important because more interstellar objects are expected to be detected in the coming years as survey telescopes become more sensitive. Internally, the coordinated campaign gave agencies a chance to practice the kind of multi-institution collaboration required when dealing with targets that must be monitored around the clock. Facilities in both hemispheres exchanged information more frequently. Software teams updated orbit solutions more actively. Photometry labs compared brightness curves to identify trends that might otherwise go unnoticed. None of this indicated an emergency. Rather, it demonstrated how the global system behaves when confronted with an object that is unusual enough to require collective attention, yet safe enough to study without urgency. Harvard's interest and the scientific divide. While major space agencies focused on the operational side of tracking 3I Atlas, the academic response developed along a different path. Universities and research groups were less concerned with coordinating telescope schedules and more interested in what the comet could reveal about material that formed around another star. Among these institutions, Harvard's involvement stood out early, not because of speculation, but because of the university's ongoing interest in interstellar objects. Harvard researchers had been studying the signatures of interstellar material since the arrival of Oumuamua in 2017. That earlier object left behind unanswered questions about its shape, structure, and acceleration, and it sparked several investigations into how objects from other star systems behave when entering the Sun's environment. By the time 3I Atlas appeared, the groundwork for analyzing interstellar visitors was already well developed. Harvard scientists saw the new comet not as an anomaly, but as an important data point in a category that is still poorly understood. Much of the academic interest centered on composition. Interstellar objects can contain ices that are uncommon or unstable in our part of the galaxy. These substances vaporize differently, reflect sunlight in unusual ways, and can affect the distribution of dust around the object. The pronounced anti-tail and the asymmetric coma in early images of 3I Atlas hinted that the comet might have a non-uniform surface or a mixture of volatiles that respond irregularly to heating. For researchers, this offered a chance to compare theoretical models with real observations. Another area of focus involved the brightness variations. Light curves give indirect clues about rotation, surface texture, and activity. With 3I Atlas, some of the brightness changes did not match the smooth progression typically expected as a comet approaches and recedes from the Sun. Harvard teams approached this not as a mystery, but as a physics problem. How does a comet formed in a different environment react to solar radiation? Which materials sublimate first? Which jets drive the non-gravitational forces? Imaging difficulties and the unusual contrast. As 3I Atlas moved deeper into the observing window, one of the most unexpected developments came from the imaging efforts. Normally, high-resolution instruments, especially those in orbit around Mars or positioned on major ground-based facilities, produce the clearest views. With 3I Atlas, the situation was less straightforward. NASA released several images captured from its spacecraft near Mars, but the results were softer and less detailed than many scientists anticipated. The comet appeared as a faint, diffuse shape without enough structure to draw firm conclusions about its nucleus or dust features. This contrast became more interesting when amateur astronomers began sharing their own images online. Using modest telescopes ranging from 20 centimeter to 30 centimeter apertures, observers in Japan, Spain, Chile, and Canada produced photographs that highlighted features barely visible in NASA's initial releases. The anti-tail showed up with surprising clarity in many of these images, along with hints of an elongated coma that suggested directionality in the comet's activity. The discrepancy didn't imply that NASA's equipment performed poorly. Instead, it reflected the practical difficulties of imaging a fast-moving, faint object under the conditions available at the time. Spacecraft cameras optimized for planetary surfaces are not always ideally tuned for distant comets with rapidly evolving dust structures. Exposure limits, tracking constraints, and the angle between the spacecraft and the comet all influence the final result. Amateur observers, on the other hand, were able to adapt quickly. They adjusted exposure times night by night, captured longer sequences, and processed their data with techniques designed specifically for faint cometary targets. This situation created an unusual dynamic. Professional facilities offered the most stable, positional measurements, while smaller, ground-based telescopes provided some of the most informative visuals. Researchers didn't interpret this as a contradiction. They simply saw it as different strengths emerging from different tools. Astrometric accuracy still depended on large observatories, but the fine dust features, including the thin anti-tail, were easier to spot in images taken from Earth under favorable viewing angles. The UN's role. The international coordination around 3I Atlas became much more visible when the United Nations released its public notice confirming the 2-month observation campaign. The announcement didn't reveal anything alarming, but it clarified how large the operation was. Beginning on November 27, 2025, the world's participating observatories would follow a unified tracking schedule designed to monitor the comet's position, brightness, and dust behavior as consistently as possible until January 27, 2026. The UN rarely comments on individual comets. Its involvement here reflected the administrative side of planetary defense coordination. The International Asteroid Warning Network operates under the UN framework, and when an exercise involves dozens of institutions across multiple continents, the organization provides the official confirmation. The statement emphasized that 3I Atlas posed no threat to Earth, but it also highlighted the scientific value of tracking it for an extended period. Interstellar objects pass quickly, and the data collected during these windows becomes part of the long-term reference for understanding similar objects in the future. One of the practical goals of the campaign was to improve the precision of astrometric measurements. When observatories collect data independently, differences in equipment, weather, and timing can introduce small variations. A coordinated schedule reduces that scatter and produces a far cleaner record of the comet's path. For 3I Atlas, with its slight irregularities and unusual dust features, this approach offered the best chance of capturing how its motion evolved over time. Each facility contributed different types of observations, building a composite data set far stronger than any single source could provide. The UN statement also acknowledged the broader purpose behind exercises like this. Planetary defense systems depend on reliable information flow between agencies. By coordinating around a real object with unconventional behavior, the network could test how quickly data moved between institutions and how effectively models adapted when the observations didn't follow standard patterns. The exercise wasn't a rehearsal for an emergency, it was an assessment of readiness under realistic but safe conditions. What scientists are learning. As the global campaign progressed, the steady stream of measurements on 3I Atlas began to reveal patterns that weren't obvious in the first few weeks. One of the earliest insights came from combining positional data from observatories across different longitudes. With continuous coverage, researchers could see subtle shifts in the comet's motion that weren't clear in isolated observations. The object's trajectory remained hyperbolic, exactly as expected for an interstellar visitor, but the fine details of its movement showed how sunlight, dust release, and rotation interacted on a timescale that shorter campaigns could easily miss. Brightness data contributed a different layer of information. When combined over several nights, it showed that 3I Atlas wasn't brightening or fading in a perfectly smooth progression. The changes weren't large, but they were consistent enough to indicate that the comet's activity wasn't evenly distributed. Some regions of the surface appeared to respond more rapidly to solar heating than others, suggesting that its composition wasn't uniform. For an object formed around another star, this possibility made sense, and it aligned with the early images showing an asymmetric coma. Dust behavior played a central role as well. The anti-tail continued to appear clearly in many amateur and professional images, and as the comet moved through different viewing angles, it became easier to trace how the dust was spreading along the orbital plane. Researchers noticed that the orientation of the dust sheet changed gradually, providing additional clues about the comet's rotation and the direction of its active jets. These observations helped refine estimates of how the nucleus might be shaped and how its rotation axis might be tilted relative to the Sun. Ground-based spectroscopy, carried out at several larger observatories during the campaign, added information about the gases being released. Early results suggested a mixture typical of comets, but with some ratios that differed slightly from many long-period comets inside our solar system. These details were not surprising, but they were valuable. They offered a rare look at how material shaped in a different stellar environment behaves when exposed to solar heating for the first time. That's it for today. Let us know your thoughts in the comments down below. Don't forget to like and subscribe for more content on 3I Atlas.